Continuity. All right. We talked about the limit of a function. Now we'll talk about it some more in the context of continuity. We're going to talk about continuity at point, left-right continuity at point, continuity on intervals and sets and domains, combining continuous functions, some familiar continuous functions, the intermediate value theorem, and the bisection algorithm. So here we go. I'm going to try to write more titles. Continuity at a number or point. Okay, so whenever we connect dots or data points or whatever, either in a computer or ourselves, we're basically assuming we're imposing continuity. Okay, and in science, you assume this kind of thing a lot. You assume that the output of something varies continuously with its input, but not always, right? So quantum energy levels and computer science models and switching that we talked about with the heavy side function, all of that's discontinuous. But for a lot of stuff, we can talk about continuous models. And so that's why this is important. Okay, continuity number. I want to read that now. Okay, we talked about discontinuities, yeah? We talked about a discontinuity being a hole or a break or a gap in the graph of a function, where you have to lift your pencil to keep tracing the graph. So this is the opposite. Okay, the function's graph has no hole or gap or break there. Or jump there. Okay? Okay, so it's not enough for your function to be defined. It has to be defined and sort of consistent with what's going on around it, and that way it's continuous at that point. You can trace the graph through the point without lifting your pencil. The output varies continuously with the input as you go through that point. And that's your official definition. In everything I'm going to say, if you change number to point, and that makes you feel better, go for it. Continuity to number. A function f is continuous at a number a if, as x approaches a, f at x approaches f at a. Okay? All right. And just, if we need a picture, y, x, y equals f at x. There's my a, very bad a. There's my a. As x approaches a, the function actually approaches f at a. Okay, exactly what we'd expected. X approaches a, f at x approaches f at a. Okay. Function f is discontinuous or has a discontinuity at a number a, or if you want at a point a, if f is defined near a, but fails to be continuous at a. Okay? And some of that wordiness is just to make it so that you don't say something's discontinuous way out of its domain. Okay? So we don't want to talk about, like we talked about the square root function. There's not much use talking about all this stuff as discontinuities. That's not very interesting. Okay? If you want to talk about, things like, holes and blowing up and that kind of stuff as discontinuity. Okay? So again, if it fails to be discontinuous around its domain, then you talk about discontinuity. Questions about that? Okay. Okay. What does continuity require? I'm going to say requires. What does it involve? F at A has to exist. So A is in the domain of the function. The limit has to exist. And the two of them have to be equal. Okay? That is all summed up by the last one, but if you think of it in pieces, it's sometimes helpful to classify things. Okay? So if you look at all the types of discontinuities we talked about, sort of jump, infinite, removable, and that funky sine 1 over x1, you should be able to see that it doesn't do this, okay, for each one of those. And again, to be crystal clear, a discontinuity is a failure to be continuous, okay? But there's some extra wordiness so that you don't start talking about boring stuff like this as discontinuities. Okay. If you're continuous, then you can get the limit by just evaluating the function. You can evaluate limit by evaluating the function. Okay? Which literally is what that says. Okay? So all those times when you saw us applying the limit laws and it was boring and you went, why did we do that? We just ended up subbing in. Well, the reason it worked in those cases was because the function was continuous at that point. Okay? Okie dokie. For example, just one example that we did before. We did a bunch, right? We did a bunch of things where sometimes subbing in worked. Sometimes we had to repair the function by some trick and then subbing in works. Here's one example. F of x, and you have this already. 2x plus absolute 3 minus x. Okay? That function is continuous everywhere. And in particular, it's continuous at 3. And so the limit as x approached 3, despite the fact that we had to do it from both sides to do it properly, because it wound up being continuous, the limit as x approaches 3 of that function was just the function evaluated at 3. Okay, because the function was continuous at 3. And if you look at its picture, you'll see that there's no breaks or gaps or anything like that. Okay? Okay. Continuity from the right or left. At a number. Okay. A function f is continuous from the right at a. A function f is continuous from the right at a if, as you approach a from the right, the function approaches f at a. Okay? And similarly for the left. So, from the right. Okay, so we got something like this. Okay, as we approach from the right, as x approaches this value from the right, let's call this a, f at a. That's the graph of f. Okay, as x approaches a from the right, the function approaches f at a. Okay, so this guy's continuous from the right. Continuous from right. Yeah? And this guy continuous from the left. Does that make sense? Okay. Okay. And saying something's continuous is the same as saying it's continuous from the right and from the left. Okay? Typically. Okay. Example. Here's your example, the floor function. Okay, the greatest integer less than or equal to a number. Okay, so everywhere that you're not at an integer, okay, this guy's continuous. Okay, it's continuous period. It's continuous from the right and from the left. It's nice and smooth and unbroken and no trouble. At the integers, you have jump discontinuities. Okay? So, at the integers, is it continuous from the right or from the left? Okay, you're gonna vote now. From the left? From the right? Thank you. Okay, good. Exactly. Okay, so at the integers, you're continuous from the right, but not from the left. Okay? Because you're approaching here, but the value is here. Okay? So continuous from the right, not from the left at the integers. Okay, so floor. Continuous, except at integers, or integer values of x, and at each integer, this is just an example, it's no more special than any other example. At each integer, the function is continuous from the right. But not from the left. Does that make sense? Okay? And my thesis advisor once taught me a cute term. You don't have to write this down. CADLAG. Continue à droite, limite à gauche, continuous from the right, and has limits from the left. And there's some functions that are like that. Okay, if you take probability, cumulative distribution functions are like that. All right. Hey kids, where is the absolute value function continuous? Is it discontinuous anywhere?
Pretty much over here, except like.
Anyone think it's discontinuous?
Yes. Yeah.
Where? That's the graph, yeah? It's continuous everywhere, okay? I don't want you confusing this with something else that we're going to talk about later, okay? That is continuous everywhere. It's joined up everywhere, okay? It may be pointy, but it's joined up, so it's continuous, okay? There's something else that isn't, but this isn't that. Okay?
Are we still on the floor function?
Huh?
Are we still on the floor?
I hope not.
Okay, oh.
That was floor. That was absolute.
Oh, okay. Okay. I was like, oh.
Okay? All right. You don't have to know this. Or any trend at all.
The catalog.
Oh, okay.
Okay. Good? Man, you'll love to talk, huh? All right. Continuity. Keep it down, people. Continuity at domains, endpoints. Oh, hold on. Okay. Okay, if we have a function that looks like this, we have a function that looks like that. I want to be able to say that that's continuous all the way from A to B. Continuous for all numbers in the closed interval from A to B. Okay, I want to be able to say that. That seems like a reasonable thing to say, but it's only continuous from the right at A, and it's only continuous from the left at B. Okay? So, when you hit the endpoints of the domain, the closed endpoints of the domain, you make an exception, okay? So the domain of a function f, if the domain of a function f begins at a number a, then we say that f is continuous at a if it is continuous from the right there. And similarly from the other endpoint, okay? So, let's say this guy's domain is literally from a to b, then we can say that the function is continuous at a, even though it only has, it's only continuous from the right at a, okay? Questions about this? This is just to make things get mad.
Could you go over that one more
I
time?
can indeed. Okay, so suppose you have a function whose domain looks like that, okay? It's closed, it's on the closed interval from a to b. So it includes a, it includes b, and everything in between. And suppose it looks like that, it's all joined up. You want to be able to include a and b in the points of continuity of this function. It just seems nice and reasonable to say that it's continuous from a all the way through b. And to do that, you say that it's continuous at a, even though it's only continuous from the right. So at the ends, you make an exception, and you say continuous from the right is enough here, and continuous from the left is enough here. Does that make sense? Okay, nothing too crazy, all right? And if you just draw the picture, it'll make sense. You don't have to worry about all that, or memorizing this, or noting stuff down. If you just look at the picture, it'll make sense. The left endpoint, it's enough to be continuous from the right. The right endpoint, it's enough to be continuous from the left. Okay, and that's to make life easy, not harder. Okay? There's a real danger of me saying left instead of right a lot today, so if you catch that, tell me. All right. Continuity on an interval. A function f is continuous on an interval if it is continuous at every number in the interval. Exactly what you'd expect. Nothing weird. And frankly, almost nothing interesting. For example, where is this guy continuous? F of x equals the square root of 4 minus x squared. CTS means continuous here. Okay? If you drew a picture of this, it would look like this. Pretend I drew this well. 2, 2, minus 2. 2, 2, minus 2. Okay, it's the upper half of the circle centered at the origin with radius 2. Okay? Where does that guy look like it's continuous? Minus 2 all the way to 2. Yeah? Okay, and it is. Good. But nothing's that easy, and pictures aren't good enough, so let's show a bit of pain. Okay, what's the domain of this thing? From the picture, minus 2 to 2.
It's -2.
What did I say?
If my -2 is less.
But it is from minus 2 to 2, yeah?
Yeah.
Apparently I have a habit of just dropping minuses occasionally, so, but only in speech. We want the domain of this thing. What has to happen? 4 minus x squared had better be non-negative. Okay, because it's inside a square root. So let's process that. Take square roots of both sides, or however you like to do this. Okay, so the domain of the function is from minus 2 to plus 2. As the picture shows. Okay, so we were asked, where is it continuous? So what do you do? Again, the ends are special cases, so we'll handle them separately. Let's do the interior first. Okay. For any A between -2 and 2, but excluding those special endpoints. What do you have to do? You have to show that the limit is equal to the functional value. The limit as x approaches a of f at x or minus x squared. Okay, you use the limit laws, and you get this, which is just the functional value at a. Hey, good, it's continuous everywhere there. Okay, it's continuous in the interior. It's ludicrously boring. Going from here to here is just limit laws. Does that make sense?
-2 plus 2b squared.
I think she asked how
The first line, a is an element of -2 plus 2, shouldn't those be square brackets?
No, I'm only doing the inside part.
Oh.
Because the definition for continuity at the endpoints is special and, right, it's only from one side. Cool? So that's the interior. You can do the boring stuff of bringing this guy in and splitting it up and going inside the power and all that stuff. And then we do the endpoints. And it's honestly just as boring. So you show that the limit as x approaches -2 from the right, it's -2 from the right. Show that that's equal to f at -2. Okay? And it is. Okay, again, use the limit laws. Okay? You slightly abuse one of the rules I told you last time, but it's okay. If you want to ask me why it's okay, you come across it, let me know, but don't worry about it. Again, use the limit laws to show this at that endpoint and at the other endpoint, similarly, as x approaches 2 from the left. Use the limit laws to show that that limit is equal to the functional value at 2. So good, it was continuous on the interior, it's continuous using the special definitions at the endpoints, so it's continuous everywhere in the domain. From -2 all the way to 2.
Wait, how come -2 would be from the right?
If you approach it from the left, you're in deep doo-doo, right? You want to approach -2 from the right.
Oh, right. Okay.
This was a bio class, I tell you. Memorize it because it's the opposite of what you think it is. So you memorize purines and pyrimides, right? Right, but look at a picture. Everything makes sense. Okay, it's math. The world works. Okay? This is someone who likes biology, by the way. Okay, that's it. All right? Use the limit laws to establish that you're continuous everywhere, and use the special definitions of the endpoints for continuity. Does that make sense? Okay, and it matches what we thought. Okay, in case you're bored to tears, hey, if you're confused, stop listening now. Okay, this is a cool function. I want to say Dirichlet, because that's what the internet told me. This function is defined everywhere, but continuous nowhere. Okay? To be able to show this, you need some real analysis machinery. You need to know the proper definition for a limit and all this. But that's interesting, okay? So if you tried to graph this thing, what would it look like? Hey, it's just for fun, it's not testing. Okay? At any point, if the point is rational, like 2, okay? Put a point at 1. Okay? If it's irrational, like pi, put a point at 0. And do that all the way along the line. Okay? The thing you're going to get, which is nothing like the stuff we see normally, is defined everywhere, but it's continuous nowhere. Which I think is cool. If you want to talk about that, let me know. You don't have to know that. Questions? Okay. Any questions about this thing? Okay, it matched expectations. We graphed draft, and we got the same thing as we did by doing it properly. Combining continuous functions to get continuous functions. Combos of continuous functions. Okay. If f and g are continuous at a, then all of these guys are also continuous at a. The sum function, the difference function, a constant times f, the product function, and the quotient function, provided you don't divide by 0. Okay, you can show all of these using the corresponding limit laws. Okay, it's really easy. If you want, I'll show you how. But these follow directly from the limit laws. It also follows from this that if f and g are continuous everywhere in their domains, then all those guys, f plus g, f minus g, f times g, f divided by g, and c times f are all continuous on their domains. Okay, that's handy. Okay, so if you want me to show you why that's true, let me know and I'll show you. But that's very, very handy. And what it means is that when you've got a bunch of functions that are continuous on their domains and you combine them appropriately, then if someone asks you where is this thing continuous, your job is easy. It's something you already know how to do. All you have to do is find the domain. And you'll love finding domains, yeah?
Not really.
Right. This is the interval version of the same thing. I don't care about it, but whatever. It's the same as the last one. You get it from the last one, okay? If the functions are continuous on an interval, then all these guys are also continuous on the same interval. And again, make sure you don't divide by 0 anywhere. That's it. Follows directly from the last thing we talked about. It's the same as the last thing, except intervals instead of points. Okay. Mercifully, a lot of the stuff we care about is continuous. Okay, all of these guys are continuous on their domains. Polynomials, rationals, roots, trig, inverse trig, exponentials, and logarithmic. They're all continuous everywhere in their domain. Okay? Continuous families. You should be able to convince yourself of this. Using the limit laws, for instance, you can convince yourself that anything that looks like x to the n and constants, that those guys are continuous, right? And then you can combine those guys to make polynomials, and so they're continuous on their domains. Okay, what's the domain of a polynomial? Everything, good? Okay, so polynomials are continuous on their domains, which is all of R. Rational functions are continuous on their domains, and the domain of a rational function is everything except for the zeros of the denominator.
Right.
Good. And all those other guys are continuous as well. If you want convincing, let me know. That's that. Okay? Okay. Okay. All right. Example. Do I really want to write that out? F of x is equal to x minus 2. This is just to make you dizzy. Ln x. Lord. Ln x plus arctan x, which, yes, is the same as tan inverse x. Provided you understand what I meant by inverse correctly. Okay? All right. We're not going to do anything, we're not going to have to graph this, we just have to talk about certain aspects of it. Every little piece here is going to be continuous on its domain. This guy's a polynomial, it's continuous on its domain. Logarithmic functions, yup. Inverse trig functions, yup. Trig functions, yup. And again, polynomials, yup. Every piece is continuous on its domain. So this whole thing is continuous on its domain. Okay? So if I ask you where is this continuous, you just have to answer what's its domain. Okay. Do that however you like. What are the restrictions here? No problem. Ln can only take, okay, how would I ask this? Where's this continuous? Where am I continuous? Okay, and I said this is the same as the domain. So this guy's continuous everywhere, its domain is everywhere. The restriction here, ln can only take positive arguments. So x has got to be greater than 0 because of that ln. Arctan will take anything, sine will take anything, that polynomial will take anything. Okay?
Wait, but
Go ahead.
like, shouldn't we look at the denominator?
Excellent, okay, and you can't divide by 0. Good? Good. So, that restriction is from there, and you can't divide by 0. So, x squared minus 4 can't be 0, and sine x can't be 0. Okay?
So essentially just like find
The
where
domain.
like it avoids D and E.
Sure.
Oh.
If by that you don't mean the limit, D and E, yeah. I put this x minus 2 in here as a trap. Don't cancel and then find the domain, okay? Find the domain first, then do all the simplifying stuff. Okay. So, what does this tell you? X greater than 0. X squared minus 4 not equal to 0. However you want to convince yourself of that is the same as saying x not equal to plus or minus 2. Sine x not equal to 0 is the same as saying x is not an integer multiple of pi. Okay, because the sine hits 0 at integer multiples of pi. Okay? Okay. So, it's continuous on its domain, which is everywhere. No, forget that. Continuous for, is that good? All x such that x is greater than 0, x is not equal to 2, the x not equal to minus 2 is already taken care of by that condition, and x not equal to an integer multiple of pi. Okay? If you want to write this as a union of intervals, continuous. There. And so on. Okay, everything positive except for 2 and all the integer multiples of pi. Where's it discontinuous? At 2 and at integer multiples of pi. Ta-da, we got a hole there, and then we got blowing up everywhere else. Those are all the discontinuities. Okay, if I ask you to evaluate, is this clear? Does this make sense? Cool. Okay. How would you evaluate the limit as x approaches something funny like e of f at x? How would you do it? You plug in.
Yeah.
Otherwise, why would I be asking you some sick, right? This guy is continuous at e. E is there somewhere. Okay? It's continuous at E. E is in this set. This is not an interval. Okay? E is in this set. E satisfies these conditions. So it's continuous at E. So that's it. That's just equal to f at E. So you just plug E into the equation, punch it into your calculator, and everything. Example. Temperature gradient. Okay. On a winter night, the air temperature outside your room is minus 10 degrees Celsius. A space heater, say I pronounced that right, keeps the air in your room at 20 degrees Celsius. Your wall is 10 centimeters thick. Model the temperature T in Celsius as a function of position x in centimeters from inside your room through your wall to the outside air. Okay, the reason we're talking about this is the temperature changes continuously over space. Okay, it doesn't just suddenly jump from one temperature to another, it changes continuously. So, suppose T is a linear function of x across your wall. On the assignment, I believe you do a quadratic version of this. Okay. Okay. Let's say 0 is the inside surface of your wall. Let's say this is your room. Goes on forever for some reason, as her room almost looked like it did. This is outside. And 10 centimeters in is the outer surface of the wall.
Does it say insicle surface?
I doubt it. Frozen fractals. Inside surface. Good? I may or may not be a fan of that movie. Inside surface, yeah? Not something you want to admit. That's your room, inside surface. Wall, outside surface, outside. Okay? And both of those go on forever to make our lives easy. All right, inside, you're at 20. Outside. What the hell is this? Okay, yeah. Outside, you're at minus 10. Okay? And between them, you've got something linear. And your job is to make this thing continuous. Okay? The way I've shown it, it is continuous.
In order to like graph these, interpret these, like kind of treat them like piecewise functions.
Uh-huh.
Okay.
Yep. Okay. Again, this looks boring and silly, but it extends to more interesting things. And you get all sorts of continuity conditions if you ever do, why would you do, if you ever do sort of electromagnetic modeling and that kind of thing. All right. The temperature is given by 20 for x values less than or equal to 0, minus 10 for x values greater than or equal to 10, and in between by what? Something linear. ax plus b, if you're in between. Okay? All right. We need T to be continuous everywhere. So we need to find A and B that make that happen. Okay? Nothing tricky at all. Okay, the way we've constructed this thing already, okay? T is continuous all in here, and all over here. The only places that it could break are here and here. Those are the only ones we have to care about. Okay? It's already continuous everywhere else. So, to make it continuous at 0, it's already continuous from the left because of this thing, okay? Already continuous from the left because of this. Okay? So let's make it continuous from the right. And once again, this is a simple version of something that could be slightly more interesting. Okay, the limit as x approaches 0 from the right of the temperature has to be equal to the temperature at 0. Okay? Or in other words, this guy here looks sort of like this. Okay? It's already filled in this way, and you need to sort of plug this over here. Okay? You need to hook it up. That's what this is. All right, the temperature at 0 is 20. The limit as you approach from the right, okay, you can use the limit laws or continuity or whatever. Let's just say the limit laws. You're going to get A0 plus B. So you get B equals 20. Surprise, surprise. The vertical intercept is 20. Okay? And the other point we are worried about is 10, so you need to be continuous at 10 as well. You're already continuous from the right thanks to this thing. So let's deal with from the left. Okay, again, what's the deal? You're filled in from the right, and you've got something linear here that you need to make sure you hook up correctly so it's continuous. Okay. We'll stop after this example, obviously. Okay, that's your continuity condition from the left. Okay, use the limit laws on that thing in the middle. A10 plus B. B we already know is 20. The temperature at 10 is minus 10. So what do we got? Minus 10 minus 20 is minus 30. Over 10 is minus 3, which you could have got from the picture. A is equal to minus 3. Okay, you fit those parameters into that model, and you've got something where temperature is continuous everywhere, and the world makes sense. Okay? Okay. That's it today, everybody. We'll continue this next time. Bring the light today. Good luck if you need to. And come see me if you want to see me. Talk about how sums and differences in products and quotients, how continuous functions are continuous. There's another kind of combination, and that's the composition. So let's talk about that. Continuous compositions of continuous functions. That's up. All right. If the function g is continuous at a and the function f is continuous at g at a, then the composite function f circle g is continuous at a. Remember, this is what we're talking about. F circle g. Okay, so we've got an input, in general x. We feed it to g, we get out g at x. We feed that to f, we get out f at g at x. And this whole guy is called f circle g. Good? So there should be nothing cryptic about the fact that g sees a and f sees g at a. That should make sense if you know how these things work. Okay, another way of saying this is that a continuous function of a continuous function is also a continuous function. And from this thing, it follows that if f and g are continuous everywhere in their domains, then, mercifully, the composition is continuous everywhere in its domain. Okay, so same kind of stories we had with sums and quotients and products and those things. Okay, To be able to use these kinds of things, you need to be able to decompose, right? You need to be able to, if you see a composite function, be able to break it up. And also, if you have sums and differences, you have to be able to break those up. And that'll become important again when we do derivatives. Okay, so what does this do? This means that if someone asks you, where is this composite function continuous, your job is to do something you've already done, and you just have to find the domain, okay, which is something you've done already. So just like before, it's reduced your problem to something simpler that you already know. Okay? All right. All right. The example. Where is f continuous? Making this hairy. The absolute value of the logarithm base pi of 1 plus cos pi x. And again, to be clear, this kind of thing makes your life easier, okay? Instead of having to think about what continuous means and how continuous works, you can just spot that all the pieces of something are continuous, and if they're combined in the kinds of ways that allow this, then the combination, whether it's sum, division, product, whatever, or composition, is going to be continuous everywhere in its domain. So your only job is to find the domain. And you can just conclude that it's continuous throughout that. Okay, where's that guy continuous? It should be obvious this is a composite function. It's a function of a function of a function. And if you want, you can say of a function of a function. Okay? So, f is a composite function. You can call it p, q, r of x. 1, 2, 3. Okay, and you wind up just applying this a few times in a chain. Okay? So even though it's not just a composite of two functions, a composite of three, you apply this enough times and you get the same result. Okay, so in this case, what's the outside function? The absolute value. Use whatever variable you want there, or a dot or whatever. The absolute value is on the outside, and this outside-inside thing, again, we'll talk about with chain rule a lot. Then one level further in, we have the logarithm base pi. And one level further in, we have 1 plus cos pi x. And if it makes you feel better, you can call this guy also a function, if it makes you feel better. Okay? Are these three things continuous on their domains? Please, yes, right? We talked about absolute value, it's continuous on its domain. The logarithmic functions are continuous on their domains. This pi was just to throw you off a bit, okay? It doesn't matter. The logarithmic functions are continuous on their domains. This is the sum of these two guys. That's a constant function, it's continuous on its domain. The trig functions are continuous on their domains, okay? And yeah, it's just transformed trig. Yeah?
Should it be Rx, not R dot?
Oh, thank you. Then I'll put a dot here. Thank you. Yeah, and again, put whatever variables you like in there. Thank you very much.
What happens if it's not, like, one of them isn't continuous? Then, like,
Then you've got to think more carefully.
okay.
And I'll try to do something in the tutorial like that. We tend not to see those examples very much. It tends to be stuff where you can use this. Yeah? Okay, that makes sense? All right. Very good. Okay, so again, everything in there was continuous on its domain, so the composition, because of this thing, is continuous on its domain. So your job is to just find the domain of this thing. Okay? And I'm not going to show you all the steps. So just find domain of f. The only thing you need to watch out for is that this guy can't take 0 or a negative argument. Okay? So this guy has got to be positive. So your only restriction, again, think it through, but your only restriction winds up being this. Okay, log has to take a positive argument. And I'm going to jump ahead here and just say that the conclusion from that is that x cannot be an odd integer. Okay? How would you figure that out? You bring the minus 1 over there. Cos pi x has to be greater than minus 1. Because cos goes between minus 1 and plus 1, that just says that cos pi x can't be minus 1. And then you look at the graph and see what that means. Okay? And that's the result. Okay? If you have trouble with this, just ask me and I'll show you all the steps. But because you're now domain experts, I can skip stuff comfortably. Okay? So the question was, where is this guy continuous? F is continuous everywhere in R except at the odd integers. Okay? And so it's discontinuous at plus minus 1, plus minus 3, plus minus 5, and so on. So it's discontinuous here. Okay? Proof by picture. Look at that. It's lovely and joined up except at the odd end. All right? Okay. Intermediate value theorem. Intermediate value theorem. Okay, let's read this out. Suppose the function f is continuous on the closed interval from a to b. Let y star be any number between f at a and f at b. Then there exists a number x star in that closed interval such that f at x star equals y star. Picture. All right. Come on, do this. Okay. Let's say that's a. B, and this function can do whatever it wants outside here. Y x, y equals f at x. Okay. That's f at a. That's f at b. Cool? Okay, so what this thing says is that you pick any number between f at a and f at b, draw a horizontal line there, this guy has to cross it somewhere. That's all this says. So for instance, if I pick y star here, and I draw a horizontal line, hey look, the function has to cross it somewhere, at least once. And that's x star. Okay? All right. So what are we saying? We're saying if f is continuous all the way from a through b, it's got to be joined up all the way from a through b. It can't possibly jump over a line. That's all this says. So if you draw a line between f at a and f at b, then this guy can't jump over it, so it's got to cross it somewhere between a and b. That's it. Okay? could say f attains every intermediate value those values would be the y stars between f at A and f at B at least once and that one time would be at x star. One of those times would be at x star between A and B. Okay? That's why it's called the intermediate value theorem. This should be reasonably as expected, okay? It's continuous, so it's joined up, so it can't jump over a line, so there you go, you get that result. Okay? And this is a consequence of a property of the real numbers, which is that they're complete, and meaning they have no gaps, okay? There are things like the rational numbers that do have gaps, okay? So this isn't obvious, but from our natural experience, we would expect this kind of behavior. But just be aware that it's a consequence of a property of the real numbers. Okay, and whenever we have a graph and we connect the dots, this is what we're doing. Okay, warning. Y'all are very quiet today. Obey the hypotheses. Let's say hypothesis. Okay, in math, hypothesis doesn't mean what it means in science, okay? It means the conditions required, okay? And the condition here is what? That the function has to be continuous on that closed interval. So that's what I mean by hypothesis here. So obey that condition. Follow the rules, okay? Because suppose f was just continuous on the open interval. Okay, suppose you had something like this. Suppose you had something like this. Okay, that guy's continuous on the open interval from A to B. But that's not good enough, right? You're not hitting all the values between FA and FB. Okay, you're only hitting, let's say, 1 or 3 of them, depending on how you think about this, right? You essentially have a jump here and then another jump here. Okay, it matters that that interval be closed. It also matters that you have continuity. Okay, so what have I got here? I've got a break. Okay, so again, you're not going to hit every value in between because there's a break. Okay? So again, make sure the thing is continuous on the closed interval and make sure the interval is actually closed. Good? If you don't understand what I'm saying here, let me know. Okay? Yeah.
Why the interval must be closed?
Okay, so suppose, like, look at this one. Okay, this guy's continuous on the open interval from A to B, but not on the closed one, right? This is f at A. This is just an example. This is f at B. We're not hitting every value in here. We're only hitting this one. Do you see what I'm saying? So this thing fails, right? So there's a reason those conditions are there. It's not to annoy you. It's because it's when it's true. Is that fair? Okay, so make sure you're continuous on the closed interval and make sure it's actually continuous. Okay. Questions? All right. Okay, we can show some funky stuff using the IVT. For example, consider a circle of any size anywhere. Okay, it could be right in front of your feet. It could be the equator of the Earth. And consider any particular moment in time. By the intermediate value theorem, there must be a pair of diametrically opposed points on the circle, meaning wherever you draw your circle, or just any closed circuit. There have to be 2 points that are like that, opposed to each other, that are at precisely the same temperature, which is wacky. Okay? I would argue this is not something you would guess at first glance. Okay? And I'll show that in tutorial. Basically, we use the IVT, and we'll use the fact that temperature is continuous over space. Okay?
So, like, you're saying that the circle is discontinuous, possibly?
No.
Oh,
No, you've got a circle or a closed circuit, and you draw it anywhere you want. Yeah?
oh, so it's still continuous because it's within this close interval.
Say that
The
again?
circle. It's still continuous.
Oh, I'll show all that. That's, yeah.
Okay.
All the idea is you draw a circle somewhere at any time. There have got to be 2 points that are opposite to each other that have the same temperature,
Alright, okay, yeah.
which is crazy, as far as I'm concerned.
That's where they before.
Okay?
It's
All right.
and then-
Okay, that's a weird kind of thing we can show. Let's do something more tame. You did not see that yet. If you have a question and I don't see you, please shout at me. Ooh, I did the bad thing. Okay, something more tame, root finding. Okay, when we have quadratics, we can just stick stuff into the quadratic formula and find their solutions. Okay? There's similar stuff for cubics, lines are even easier, and there's similar stuff for quartics. But for quintics and above, there's no formula. And when you have stuff that isn't a polynomial equation, it's even weirder, okay? You can only get analytical solutions in very, very, very special cases. So what can you do when you want to find the solution of an equation? For example, suppose you want to solve cos x equals x. Okay? We can't do this exactly. Okay? Try, there's no way to solve this thing analytically. So let's do this instead. Let's define f at x equal to cos x minus x. So now the solutions of this are the zeros of this. Okay? Solutions of this are zeros of this. Okay? Let's see if we can say that there's a zero or a solution between two values. Okay? We won't get the exact one, but at least let's get an interval where a zero must exist. And then what I'm going to try, I'll show a solution exists between 0 and pi. What's a pi over 2? Pi over 2. Okay? Alright, so we're going to use the intermediate value theorem. Okay? Is this guy continuous on the closed interval between 0 and pi over 2? That's continuous. That's a trig thing, that's continuous. When you take functions continuous on their domains and subtract them, you get a continuous function on this domain. This thing is continuous everywhere, so it's certainly continuous on the closed interval we're looking at. You always have to check. F is continuous on the real line, so certainly on 0 to pi over 2. Okay, always check. Okay. Now what do we have to do? We have to see what f at a and f at b are. A in this case is 0, b in this case is pi over 2. What's f at 0? Cos 0 minus 0. Cos at 0 is 1, so that's just 1. F at pi over 2 is cos pi over 2. It's very lazy. Cos pi over 2 minus pi over 2. Okay, pi over 2, the cos hits 0. So it's 0 minus pi over 2. So So it's just minus pi over 2. Okay, which is good news. This guy's positive. This guy's negative. What does the IBT tell us? It tells us that because we have that continuity on the closed interval, between 0 and pi over 2, we're going to hit every value between f at 0 and f at pi over 2. Because this guy's positive and this guy's negative, in particular, we're going to hit 0 at some point. Okay? So by IBT, f at x star is equal to 0 for some x star between A and B. Okay? Okay, does that make sense? All right, and if you look at a graph, it should make sense that there's indeed an intersection somewhere in there. Okay, but notice this is different from graphing, okay? All we did was we evaluated the function at 2 points. We didn't have to evaluate it at loads and loads of points to draw a graph. We just evaluated at 2 points, which is easier on, say, a computer or a person than drawing a graph. Okay, so all we needed was continuity and those 2 points, and we could find that there was a 0 in there. Okay? And a 0 of f means a solution of that. Okay? Yep.
Can't you figure out that f is continuous?
So, what do we got? X is continuous, because it's boring enough to be continuous. This is a trig function, so it's continuous from last class's stuff. And if you have a combination, plus, minus, times, divide, whatever, of functions continuous on their domains, it's continuous on its domain, right? And the domain is the real line. Okay, so it's continuous on R, so it's certainly continuous on a piece of R. Cool? Okay. And by the way, what did this tell us? This positive, it told us that cos was above x over here. And this negative told us that cos was below x, okay, over here.
And we're supposed to get a positive or negative.
If you want a 0, yeah,
Okay.
you should, right? Okay? So cos went from being above x to being below x. So at some point they switched. And because they're continuous, that switch means there's an intersection. Okay? So continuous functions can't change order without crossing. And continuous functions can't change sign without crossing 0. Okay? Whereas discontinuous functions can change sign when they cross 0 or at their discontinuities. Okay? For instance, 1 over x. 1 over x looks like, whoa, 1 over x looks like that. Okay? It changes sign, but it doesn't cross 0 because there's a discontinuity there. Okay? But continuous functions can't change sign without crossing 0. And they can't swap their order without crossing each other. Okay? There's a bunch of other stuff that follows from this. I may do it in tutorial. Okay? All right. Get my attention if you need it. Bisection algorithm. This is an application of the intermediate value theorem. Okay, suppose it's not good enough to know that there's a 0 in here somewhere. Triple check. Okay, suppose it's not good enough for you to know there's a 0 in here somewhere. You want a decent approximation of a 0. So you have to do something else. And this is one such thing. It's an iterative, meaning that. You do steps over and over again, numerical procedure. Okay, and I've written it all out there for you. Have a read. But I'll do an example and hopefully that'll be clearer than that. Okay? So here's an example. Same one. Solve cos x equals x. Accurate to within plus minus 0.125 and start on the interval, how about this? Let's just say start with left endpoint, using that notation, okay? Left endpoint 0 and right endpoint 1. Okay, what we're going to do is we're going to have an interval where this root must be, and then we're going to narrow down that interval, okay, as far as we like. Okay, and we're going to start with the interval from 0 to 1. Before we did 0 to pi over 2, but here we'll do from 0 to 1. Okay? And how would you know this? Divine intervention, someone tells you, you guess, you think about it, some sort of search. Somehow you have to have this initial guess of where the interval is, where this root must be. Okay. As before, we're going to define f at x equals cos x minus x. So again, solutions of this are just zeros of this. So then we can use IDT. And again, check for continuity. F is continuous on, in this case, 0, 1. So it's fine to keep going. Okay? All right. Okay. Again, do have a read through that, but I'll do it without being quite so verbose. Okay, these are your x values. Down here I'll write the signs of f at x. And here we go. Okay. Evaluate that function at 0. Okay, we already did that. It's positive. If you evaluate at 1, you're going to get some negative number. So evaluate it and make sure it's negative. Okay? Good news. All right, one's positive, one's negative. You're going to have a crossing somewhere in between them.
So you just plug in like.
That's right. You plug in 0 into this, and you plug 1 into this, and check their signs.
Like 0 into 1 again? Like the same one, and then we basically do the same thing as the
As
one
that.
on that side.
That's
Okay.
it. Okay? So it goes from positive to negative, so at some point it's got to cross. Okay? So good. That's sort of your first preparatory step. Okay, so your preparatory step, check for opposite signs. Okay, check that the thing you're starting with actually has opposite signs of f so that you'll be guaranteed to cross somewhere in between. Okay? All right. Okay. Now what? Okay. It's called bisection. Let's bisect this interval. Ta-da, 0.5. Okay, again, plug 0.5 into there. See what you get. Okay? The sign of what you get is going to be positive. Okay? So again, bisect the interval, evaluate there, and you're going to get something positive. Okay? And now your job is to see, okay, what have you narrowed it down to? You're not guaranteed a 0 between these two guys. Okay, they're both positive. There might be one, but you're not guaranteed one. Between these two guys, you are guaranteed a 0 by the intermediate value theorem. So there you go, you've narrowed your interval down. Okay, that's the preparatory step. This is iteration 1. Okay, bisect, evaluate, and then narrow down the interval. Okay? And you'll notice the interval got narrowed by a factor of 2. So there you go. Okay? The crossing is between those two guys. Okay? You're not down to the precision you want. Go again. Okay? You know you need to be in here somewhere. By the way, if this evaluated as 0, hey, you're lucky. You've already found your solution. You can stop there. Okay? But you didn't here. That would be very lucky. So now, you've got a new interval. Do the same thing. Bisect, 0.75. Evaluate there. And it's going to be negative there. Okay, again, plug 0.75 into that guy, see what the sign is, there you go. You're not guaranteed a 0 between these two guys, you are guaranteed a 0 between these two guys. Iteration 3. Iteration 2.
It means that you
Okay? Hey, there you go. You're guaranteed a 0 between those two guys. The circled one on the right is just under 0. Okay? All right. You've reached the necessary precision. You've reached the required precision. So you can stop there. Okay? All right. So how can you cite your answer? Okay, so again, you know there's going to be a 0 between these two guys. There might be others elsewhere, but you know there's one in here. Okay? So, how can you say, what can you say your answer is? There's going to be a solution, at least one. In between these two guys is 0.625. 0.625 plus minus 0.125. Okay? You know there's going to be a 0 in here, so it's going to be the middle plus or minus half of the width of the interval. Okay? Okay? There's going to be a 0 at that red dot plus or minus the width of that interval, half of the width of that interval. Or you could say there's a solution on 0.5 to 0.75. Okay, and you see that was the necessary precision. Okay? Those are both reasonable ways of stating your answer, unless we ask you for a particular form. Yes, ma'am.
And for the second solution, 0.5 to 0.1, it has to be a closed interval, so we can use square brackets.
Here?
Yeah.
Yeah, the reason I did this, and I did a similar thing over there, is that because this is positive and that's minus, you know those aren't the solutions. So I opened it. Okay, thank you. All right, yes, ma'am.
But in the first case, aren't you including 0.5?
In which case?
Like solution 0.625 plus or minus 0.1? It doesn't remember.
No, no. It's almost the same. Yeah. I don't know of any way of writing something like this and making it look open, so that's the best you can really. Okay? Does that make sense? Just IVT over and over and over again. That's it. Okay, until you get to where you need to be.
How do you know where you need to be?
Because someone will tell you.
Oh, you're right.
Okay, and you're going for that. Okay, the width of the final interval has to be twice that allowance. Okay? All right, notice your approximation error, okay? The sort of interval that you're in gets halved each time, okay? So for each, 1 second, so for each iteration it becomes halved, okay? So you improve exponentially with the number of iterations you do. So you just keep doing iterations, you get better and better and better, okay? Exponentially. Yes, go ahead.
In the question, will it indicate what to start with?
It seems likely. Yeah, otherwise we could get all sorts of stuff, yeah. Typically, yes. No guarantees, but typically, yes. Okay? Or if you're desperate, you can just draw some sort of a sketch and then see what seems reasonable, where it's above and below. Okay, there's other ways of looking for zeros, okay? There's something called Newton's method, which we're going to talk about later. There's also something called fixed point iteration, which is fun for something like that equation, and I might show you that in tutorial. Okay? Questions? We're done continuity. We're done limits.